Hello, welcome to this video. We're going to talk about series and sequences, and we're going to make a transition from general series and sequences to more specific ones like arithmetic progressions and geometric progressions. All right. So before we begin, let's define and let's get an idea of what a sequence is and how it's represented in mathematics. Okay, so a sequence is basically a set of numbers. An arrangement of numbers in a definitive order according to some rule or some sort of specified kind of way of writing them. So what I mean by that is, let's consider a sequence like so 2, 4, 6, 8, 10, 12. Okay, so this is a sequence, and what we notice about the sequence is that there are 6 terms, and the thing about this is it can be represented in some format. That is to say, if the 2 is, say, the first number in the sequence, 4 the second one, and similarly 12th is the sixth number in the sequence, then what we can do is we can actually have a formula for the general representation of a number. That is to say, if I have to write AI, a sub I, that is the ith term in the sequence, I can basically write 2 times I. Now note that this works in the sequence. So if I have I to be, say, 4, if I equals 4, then AI equals 8, which is the case as what you see here. So if you go from 1, 2, 3, and 4th term, that happens to be 8. So the nice thing about sequences are the fact that they can be represented in a formula. And this relation is what is important, and that is what distinguishes it from just a linear arrangement of numbers. Okay, so this is what a sequence is. Now, we have more complicated ways of representing a sequence. For example, a sequence can also have the form AI equals n square, well, the index is I, so I should use I, so that's I square plus 1. And what I mean by that is, if I have to write what this sequence represents, I have to start from, say, I in the range 1 to, say, 5. Then this clearly gives me all the information I need to know my sequence. All right, what I mean by this is I'm considering the sequence of this formula, and also I'm considering only the terms in which the index I goes from 1, 2, 3, 4, and 5. 1 and 5 there are included because of square brackets. Right, so what I mean by that is, if I have to list down all the terms in the sequence, I should start with 1. So if I use 1, you notice 1 square is 1, and 1 square plus 1 is 2. If I do the same thing for 2, we have 2 square plus 1, which is 4 plus 1, that makes 5. And we do that for 3, that makes 3 square plus 1, that gives you 10. And then we go on to 4, 4 square plus 1 is 17, and 5 square plus 1 is 26. So notice that this is a different sequence from the one that we considered before. In fact, the difference between all the terms is also not constant, but it is still a sequence. Okay, so the idea from going to here to there was to introduce you to the fact that sequences can be more complicated than just simple linear relations. They can also be quadratic relations, as you see here. And there's nothing limiting us to even call sequences of this form. So if I say AI equals sine of pi I plus 1, all right? So this can be a sequence as well. Now, if I have to specify where my sequence starts and where it ends, I can say it starts from, say, -1 and goes up till +1. This is also a sequence, and if I have to list down all the terms, well, that would make it so that would make it the following. So sine of minus pi. So if I write it for -1, then notice sine of minus pi is +1 will give you some specific value, and you can evaluate this using your calculators. Okay, if I remember correctly, the sine function goes something like this, and this is sine of x, and this is x right there, and we notice at minus pi and plus pi, right, like so, sine actually takes 0 value. So this gives you 0 plus 1, which is 1. So that is the first term of the sequence. Then for sine 0, pi plus 1 is this, so sine 0 is 0 again, and that makes 0 plus 1 to be 1 again. And if I do the same thing for well, plus 1, I get the same value again. So even though this is a rather straightforward sequence where all the terms are 1 and really nothing's changing, they surprisingly come out from a very complicated formula, or a rather more complicated one from the ones we considered before, these two. All right, so sequences can take weird forms, so that is what we will investigate in the further videos. Before I move to more specific sequences, the ones that are more studied, which are called arithmetic and geometric progressions or geometric series, I would also like to introduce you to another way of representing a series or a sequence. So if I get rid of that, and I'll just recap what we have done so far. I've told you that sequence or series is just a set of numbers which are given by a formula. So we can have am to be some function of m. This is what we call the functional way of representing a sequence. We can also have another way of writing a sequence that is a function of am plus k prime, and so on up till am plus k n prime. You can have as many terms as possible. Now, this may seem very complicated, but what it essentially is telling you is that if I want to figure out what my mth term is, it can also happen that it can be a function of the kth term from the mth term, and as well as the k prime term from the mth term, and so on and so forth. That is to say that if I have a sequence of, say, a few numbers, all right, so if this is my mth term, and this is, and say, this is my m plus k term, this is my m plus k prime term, so on and so forth, then I'm saying am can be related to am plus k. It can also be related to am plus k prime. All right, so that is what we call the recursion. All right, pardon the handwriting right there, but what I mean by that is, rather than giving it a functional form of the index, as was in the case of a previous description of a sequence or series, here we're actually giving it a form that relates to other terms in the sequence, and with the help of that we can evaluate all the other sequences, all the other numbers in the sequence as well. A very good example of a recursion that gives us a sequence is the following. So if I have am equals am minus 1 plus am minus 2, given that a1 equals 1 and a2 equals 2. Now, if you haven't noticed this already, what's special about this is the fact that this gives you something which is very popular in today's time, or at least in the mathematical world, and what we used to call the Fibonacci numbers. And this comes out as follows. So if, I'm sorry, a2 is 1 again, I'm so sorry about that. So what I'm saying is, if I have to list down the Fibonacci numbers, or the numbers given by this recursive formula, I must start with a1 equal 1, a2 equal 1 again, and for a3, I basically need to plug m equal to 3, that gives m minus 1 equal to 2, and m minus 2 equal to 1. What that means is, if I have to figure out a3, I must add the second term as well as the first term. And when I do that, I get 1 plus 1, or 2. So that's my a3. Similarly, I can write a4, which is a3 plus a2, and that gives me 3. And a5 similarly would become 5, and a6 similarly would become, well, 5 plus 3 is 8. And similarly, a7 can be written as 8 plus 5, or 13, so on and so forth. So you see, these, sorry about that, these are my Fibonacci numbers, and they continue in this fashion. All right, so what I'm telling you is that at times you have functional representations, but at times you can also get, or also have, recursive relation and recursive functionalism, in the sense that the numbers are related to each other rather than the position where they occur. Okay, so those are just two ways in which you can write a progression, a series, or a sequence. All right, I hope this video made sense, and upcoming videos would include things like arithmetic progressions and geometric progressions. We'll work out very many examples that will help you clarify and get a really good understanding of what goes on in those progressions. So all the best and have fun.